So say we have this simply supported beam with a point load applied at midspan. What we're interested in finding out is what value of load will cause the beam to yield, to begin to yield, right? And then what value of that load will cause collapse. So again, I've got the idealized stress strain curve here, right? As we all know, it's not going to be perfectly linear in the plastic region right there, but just to idealize it for the purposes of defining these things. We have this first portion, as we talked about last time, represents the elastic energy. And then beyond that, the area under the plastic region represents the plastic energy. So we also have here this point representing the onset of yield. And then ultimate failure at the end. So I'm going to make a note here, right, that what we're looking at, or what we're focusing on in this class, we'll look at the condition associated with the onset of yield, but we're going to take it all the way to ultimate failure and look at that condition as well. So once we are at this point of ultimate failure, the elastic energy is small compared to the total energy or the plastic energy. So we're going to ignore the contribution of elastic energy when we are considering this state, right? So we can just neglect that and focus on the plastic energy. All right, so we sketched the shear and moment diagrams associated with the plastic, or with the elastic load case. All right, it would be our shear diagram, something like this. And our moment diagram would be linear with a maximum value of PL over 4. So I'll note that our maximum moment is PL over 4 and occurs at midspan. Where X equals L over 2. The initial yield will occur at the end of the elastic response, right up here. And we would call that, again, the onset of yield. So that's where the normal stress reaches a yield stress. And in this context, right, so I guarded against this in the previous lecture, but I didn't in this one. But that's because when we're talking about the context of beams, the only relevant stress is in the longitudinal direction, right, for beam bending. So that's your sigma x. So in this context, the sigma y represents the yield stress. Don't confuse it with stress in the y direction. In the last lecture, I made a distinction because that was much more general, where you apply those concepts to systems that might have stress in the y direction. So at the onset of yield, that means the extreme fibers have just started to yield. And that would occur where the moment is maximum at mid-span. All right, so for that condition, we have our stress distribution along the depth of the section, right? So the cross section is shown above with a depth of 2c and a width of b. Neutral axis at the centroid. And the moment associated with this onset of yield condition is going to be the yield moment. So I'm going to say m is equal to my to cause the extreme fibers to reach that sigma y value. So we have my times c over moment of inertia I is going to be equal to the yield stress, right? Because c is that vertical distance to the extreme fibers in either direction. For a solid rectangular cross-section, moment of inertia, we'll write it in terms of the dimensions. B times the height is 2c, and that gets cubed over 12. So my, we can then write in terms of the cross-section dimensions and the normal stress. So my is equal to the yield stress times B and 2c quantity cubed divided by 12c. So that gives you the calc for the yield moment. And that simplifies to 2/3 BC squared times the yield stress. Now, quick gut check on the units, right? BC squared gives you, let's say it's in inches, it'll be inches cubed, and the normal stress will be, let's say, in kips per square inch. So that gives the correct units for a moment, so that checks out. So we can then write our yield moment in terms of the applied load, right? So we want to relate that moment that would cause yield to the applied load, because remember our first question is what value of P causes yield, and then what value of P causes collapse. So to start, we're focusing on yield. So we have my, and then we have our moment diagram value, right? This is where the maximum moment occurs. So we'd set my equal to py times L over 4. Solving for py, we get, and plugging in our values for my above, we get 8/3 times BC squared over L times the yield stress. So that gives us the yield force. In terms of the cross-section dimensions and the yield stress, right? All right, so if we continue to increase the applied load beyond that initial yield, then what happens is more depth within the cross-section will reach that yield stress, and the stress distribution will begin to look more like this, right, where you have a plateau at sigma y. So in that in-between phase, our moment is greater than the yield moment, right? And we also know, right, since we have our moment greater than the yield moment, we also know that the moment is equal to the integral over the area of the normal stress times the moment arm, which is the variable distance y. All right, so for a constant width rectangular cross-section, dA can be substituted with b dy. Right, since b is constant. So in our stress distribution, we can break it down into two sections, right? For, well, first of all, it's symmetric, so we'll just look at one side. But within that side, we've got two sections. We've got the section that has yielded and the section that has not yet yielded. So from the section that has yielded, we have a resultant normal force, F1, and that's equal to sigma y times C minus A times B. So that's just taking the normal stress times the area over which it's acting. Similarly, for the not yielded portion, we have just a triangle, so that's 1/2 times sigma y times A times B. And that's for variable distance y between 0 and A. So back to evaluating our moment, right? For the integral, since we have a symmetric distribution, right, we can take advantage of that and say, okay, half the moment will be associated with the integral over the area of the top half of the stress distribution. So we'll say m over 2 is equal to the integral from 0 to A of the unyielded portion. So that's going to be sigma y minus y over A, all of that times B, and then times y dy. And then the integral over the area of the yielded portion. So that'll be the integral from A to C of sigma y times B dy. So from that, we get m is equal to bc squared over 3 times sigma y. And then in parentheses, we have 3 minus a squared over c squared. Or we can rewrite that in terms of the yield moment, right? So substituting in our relationship from the previous page, which I'll copy down here in a moment, that would give us m is equal to 1/2 times the yield moment times, in parentheses, 3 minus a squared over c squared. And that's coming from plugging in my is equal to 2/3 BC squared times sigma y. Right. So with this relationship, we can determine, if we know the applied load, right? We can determine the moment from that applied load. And then we can also determine how much of the cross-section has yielded and what has not. So in short, all right, we can determine the lowercase a if P and M are known. And then also note that when A is equal to 0, that represents the condition where the cross-section has fully yielded, right? So that represents the state of ultimate failure. And that is what is sketched down below, where the entire cross-section has a rectangular stress distribution, right, of magnitude sigma y. So all fibers within that section at that location on the length of the beam have yielded. Mu represents the ultimate moment. And our resultant forces are simply going to be sigma y times BC. So we have our moment, set that equal to the ultimate moment, and we know that's just going to be BC squared times sigma y. We don't have to go through the integration. So that's equal to 3/2 times my. And then it follows that our force is equal to the ultimate force in this state, and that's going to be 4 BC squared over L times sigma y, which is going to be 6 times the yield moment divided by L. All right, so that's just plugging in M equals PL over 4 to get that connection between the moment and the applied load. So when this state has been reached, this represents a plastic hinge. So the beam has formed a plastic hinge at the location of the maximum moment, which in this case corresponds to the location of the applied load P, and the collapse mechanism has begun. So I'll sketch the shape of the whole beam up on the side, and then we'll focus on the right side of the hinge, which is what's already drawn in the notes. So let's say beam forms a hinge. When P reaches ultimate, and the collapse mechanism begins. So if we consider the entire beam for a second, and we have our simple supports and the applied load, P. All right, basically what's happening is the portion of the beam that has yielded is what I'm shading in. That's a little bit exaggerated there, but you get the idea. So as you go along the length of the beam, right here, nothing has yielded yet. Here, you're in that in-between stage, right, where some of the fibers have yielded, but not all. And then right here, this is where it's fully yielded and that plastic hinge has formed. So this point along the length of the beam can no longer resist moment, right? It can't transfer moment. It's going to behave as a hinge. And so the deflected shape, right, will be the collapse mechanism. So I'll just draw the center line, and it's just going to look like this. All right, imagine a hinge right there. All right, so if we focus on the right side of the hinge, and we get a little bit more detailed, we can determine exactly how far along the length of the beam we have some yielding occurring, right? So we're looking to identify this point where we can distinguish between the portion of the beam that hasn't yielded at all along the length, and then the portion that has some yielded fibers. So that's just done using geometry. We know that we have the ultimate moment at this point, all right? And then at the point that we're trying to find, it's where the onset of yield has just occurred, right? So that's where you have my, and that's where you have mu. So we can simply relate mu over half the beam length, all right? We're just using similar triangles here. Since, and by the way, this is taking the right side of the moment diagram, right? So I'll make a note of that. So that's the right side of the moment diagram, which, remember, was linear. Set that equal to my over the distance that we're trying to find. All right, so that's what we're solving for. And then we can substitute in our relationship from above, where my is equal to 2/3 of mu. And then, so solving for d, we just have d is equal to 2/3 times L over 2. So d is equal to L over 3. So for this configuration and this loading, right, with the load at the center of the beam, a full third of the length, let's see, or what am I saying? All right, so a full third of the length of the beam on either side of that hinge has not yet yielded, right? So that leaves a third of the length of the beam in the center that has experienced some yield in its fibers, right? Okay, so now that we have investigated the process of reaching that fully yielded state, the plastic hinge, we're going to investigate the process of unloading. All right, so if you have loaded a beam to that point, then using the understanding that unloading is an elastic process, we have our normal stress equals to my over I, that's the elastic relationship. Set that equal to mu times y over I, and then substitute in our relationship mu for my, so 3/2 my times the variable distance y divided by I. And then making our substitution for my in terms of the cross-section dimensions, we have 3/2 times 2/3 BC squared times sigma y times the variable distance y, all over moment of inertia, which is also b times 2c cubed over 12. And that simplifies to 3/2 times the yield stress times the variable distance y over c. So this right here represents the unloading stress. Now we'll map this out visually because I think it's easier to comprehend with the stress diagrams on the cross-section. So down below, I've pre-sketched the loading condition to the point of plastic hinge. Now, next to it, I'm going to sketch the unloading stress. All right, so I'll place the neutral axis and align it with the other sketch here. And then I'll draw the distribution. I'm just going to try to align it vertically as well. So that's pretty close. All right, so we just determined that the unloading stress magnitude is going to be 3/2 times the yield stress, and then this gives us the linear distribution, right? The variable y divided by c. So at the extreme fiber, when y is equal to c, that value is going to be 3/2 times sigma y, right? And that's going to be true at both ends. And it will be 0 when y is equal to 0. So we have our linear elastic unload right there. And so if we superimpose these two states, right, add them together, we're going to get what we call the residual stress. So, say like that, and then we're just adding the points together. So we have 3/2 sigma y minus sigma y. So we'll have 1/2 sigma y at the extreme fibers. And then at the neutral axis, we're going to have a stress of sigma y. This is clearly not to scale. It's going to look something like this. right, where we have, here we would have tension at the top and compression at the bottom, and then somewhere in the middle it would switch again, right? So we have a distribution, something like that. So if we want to write the equation for this residual stress distribution, we can do that. So that's going to look like this. We'll call it sigma r, and that's equal to sigma y minus 3/2 times y over c times sigma y, or that yield stress, sigma y, times, in parentheses, 1 minus 3/2 y over c. And that's the residual stress distribution. Which is what we just sketched. We can also determine the moment that corresponds to that state. So again, taking advantage of symmetry, we only need to focus on 1/2 of the cross section. So we'll look at 1/2 and say 1/2 times the residual moment is equal to, since the yield stress is a constant value, we can bring that out front of the integral. Same with the width, since we have a rectangular cross section. And we'll integrate from 0 to c for the top half. And within the integral, we have 1 minus 3/2 times y over c to represent that component of the residual stress. And then for moment, we also have to include the moment arm, which is the variable distance y. So that evaluated gives us the yield stress times the width of the cross section. And then in brackets, we have variable y squared over 2 minus 3/2 times the variable y cubed over 3 times 1 over c. And that's evaluated from 0 to c. And when you do that, that's equal to 0. Who was expecting that? So ultimately, these residual stresses are permanent, right? There's no moment associated with this state. Once you have loaded the beam or structure to the point of a plastic hinge and then unloaded it, you will have these permanent stresses. If you continue to then cycle through loading and unloading, then the residual stresses will just keep increasing until eventually the material will reach failure and it will fracture. So some of you have seen this before in other classes, yes? Or talked about loosely related things anyway?
In steel, we didn't talk about residual stresses necessarily. We just used work energy method, MP theta equals P delta.
Okay. Yeah, well, we will do that next. So, yeah, all right. So I'll just note down here, summarize what I just said. Residual stresses are permanent. right, so then at the bottom of the page, I've just got kind of a general note related to identifying the collapse mode. So in this class, what we're going to do is first use the energy method to determine what the collapse mode is, and then we will confirm that using equilibrium. All right, so to demonstrate this, right, we're going to consider the same simply supported beam, and we're going to increase that load that's applied to the ultimate load as shown here. So at that point, the hinge will form and collapse will begin. We already sketched previously what that collapsed shape will look like, right? It's going to be like this. So at that location, at the plastic hinge, we have the ultimate moment, right? So we know the internal moment there is mu. That distance vertical distance at that location, I'm going to call that delta. And the angles at each support, we'll call that theta 1 and theta 2. Now, for this configuration, since the load is at the center, we know that the two angles will be the same. So theta 1 and theta 2 are equal. We'll just call them theta. And we're also going to apply the concept of small angle theory, which says you can equate an angle to the tangent of the angle. So we'll call theta and say that's equal to delta divided by L/2. So we'll define the external work. And I know we're almost out of time, so we'll have to finish this up next time, but we'll just get it started. The external work is equal to the load, the applied load, times the deflection through which it acts. So that would be Pu times delta. And we can make our substitution and write it in terms of theta and L. So Pu times theta L/2. And then we'll write out the strain energy and stop there. So the internal strain energy U is equal to, internally we have the ultimate moment at the plastic hinge, right? And that moment acts through a total rotation of theta 1 plus theta 2. So you can think of it as this side of the hinge, mu acts through theta 1, and on this side of the hinge, it acts through theta 2. That's sort of how I'm going to write it out. So mu times theta 1 plus mu times theta 2. And since theta 1 and theta 2 are the same, that's going to be 2 mu theta. And then so for total work, we're going to set the internal work equal to the external work. And then we can solve for the magnitude of Pu that would cause collapse, right? So we'll do that next time. And then we will continue that with more interesting beam configurations.